Hi there, grade 11s. I'm going to, in the next series of videos, work through force diagrams and free body diagrams. And we are going to look at different scenarios or cases where we will concentrate on how to calculate friction. My examples are going to be abstract in this set of videos, just to get you into the basics. So the first thing we need to work with, so we are going to look at friction. And there are two types of friction. We've got static friction and we've got what we call kinetic friction. Both these frictions are dependent on the types of surfaces in contact. So type of surfaces and the normal force. The force that the surface on which the object is resting exerts on the object. So these two factors are the main contributors to affecting friction. In the first example, first set of examples in this video, we are going to have object placed on a flat surface. The first scenario is that the object is placed on a flat surface and there is no applied force. Fa is the symbol for applied force that I will use. So let's draw this. I've got my flat horizontal surface. I've got an object resting on the surface. Now we need to identify the forces acting on the object. The first force that I would identify is the force of gravity. That is the force that the Earth exerts on the object straight down to the center of the Earth. The next one is the force of the surface on the object. And in this case, the weight of the object, the gravitational force, is calculated by using mg. In this case, the normal force acting on the object will be balanced out by the gravitational force. So the magnitude of the normal force would be the same as the magnitude of the gravitational force. As there are no applied forces acting on, no applied force acting, there is no intention to move. If there's no intention to move, then the friction would be 0 newtons. So this is the first example. You are welcome to pause or stop the video at any moment that you need to take notes. Right? Next example is where the object is on the flat or the horizontal surface and there is an applied force. So the second example is object on horizontal surface. There is an applied force, So the applied force is not 0. There is an applied force. In this example, the object will still be stationary. So there is our object. Let's identify the forces acting on the object. Gravity, normal. Once again, these two forces in the vertical plane will be in equilibrium. So the normal force would be equal to the gravitational force in magnitude, in size. Now, it doesn't matter whether you consider a pulling force as the applied force, or whether you consider a pushing force as the applied force. It would be an applied force, right? So either one, pulling or pushing, would be the applied force. The moment you have an applied force acting on the object, there would be an attempt to move the object. If there's an attempt to move the object, there would be a friction between the surface and the object surface. So if the object is stationary, then the friction would be called the static friction. So here we have a static frictional force. My arrow is not completely correct though. If the object is not moving, the horizontal pulling force or pushing force would be in equilibrium, kept in equilibrium by the static force. So the arrow for the static force should be more or less in your diagram be the same length as the arrow for the pushing force or the pulling force. I'm going to remove the pushing force. I would prefer one to be acting on the object. Now, the question is, what is the magnitude, the size of the frictional force? Now, this is a static friction, and it is in equilibrium with the force that acts in the opposite direction, which is your applied force, in this case, a pulling force. I haven't done it in the first example. This is a force diagram. I want to draw the free body diagram for the situation. Free body diagram. That is the diagram you obtain by joining all these forces, tails together. So here we go. The gravitational force, Fg, the normal force, Fn, the pulling force, F applied or F pull, and the frictional force. All the forces are in equilibrium. Right, this brings us to the end of this example, because the way I will calculate the static friction before the object starts moving is by equating it as equal to the pulling force. The third example we will do where the object will start or attempt to start moving at that moment. So here we go. The object is still on a flat horizontal surface. Now the object, there is an F applied. It is a non-zero F applied, and the object is about to move. In this case, the static friction will be the maximum static friction. Place our object on a flat surface. The gravitational force will act down on the object. The normal force will act up on the object, equal in magnitude to the gravitational force because the vertical forces will cancel. Let's say this example, we're going to draw a pushing force. So there's an F applied is a push. The friction will oppose the force that pushes. It will oppose the intention to move. So the frictional force would act opposite the applied force, and in this case, it is the maximum static friction. Now here things are starting to become a little bit more complicated because the F push is in equilibrium with the Fs max. So if I want to get Fs max, it would be equal in magnitude to the pushing force or the applied force. With Fs max, though, there is another equation that we can calculate the Fs max with. So depending on the type of questions and the values that were given, you would either use either of the equations. Fs max is in a relationship to the normal force, and the coefficient of static friction is the constant in this relationship. So this is another way to calculate the maximum static friction. If I have the coefficient of static friction, I can multiply it by the normal force, because the coefficient of static friction gives us the ratio between the maximum static force and the normal force. The normal force determines the size of the friction. In this case, the normal force has the same magnitude as the gravitational force. I can use mu s times the mass times gravity here, gravitational acceleration, to get maximum static friction. Right. In the next example, number 4, I am going to have the object moving on the flat plane. So we've still got the same object, but now it's moving at a constant velocity on the horizontal plane. In this case, the applied force is non-zero, and the friction is kinetic friction. Here we go. Our object will have gravitational force acting on it, a normal force acting on it that is equal in size to the gravitational force, and we'll have an applied force, whether it's a pulling force or a pushing force, it doesn't matter, and there will be a friction. Now this friction, if the object is moving at a constant velocity, it means that the forces are in equilibrium. It means that they're balancing each other out. Then this friction would be equal in size to the applied force. Fk would be equal in magnitude to the applied force, whether it's a push or a pull, it doesn't matter. But with kinetic friction has a relationship to the normal force that is a constant. There's a constant relationship between the kinetic friction and the normal force. And that constant is defined as the coefficient of kinetic friction. So Fk has a relationship to the normal force. In other words, Fk is equal to mu k times the normal force. And what is the normal force in this case? Because the vertical forces are also in equilibrium, it is equal to the gravitational force, which we can calculate as mass times gravitational acceleration. So here we go with the kinetic friction Fk as equal to mu k times the mass times gravity. So with kinetic friction, there will be two possible equations to use. This one, if you have information to use that one, and this one, if you have information to use that one. I'm going to stop this video here. I'll move on to the next two examples in another video. Thank you very much for watching. I hope these videos are helpful.